So let's see here. So if we have, suppose that, let me just draw a picture here. Suppose that there's P. Suppose there's P in the intersection, right? In principle, this P in the intersection, in practice as well, the P in the intersection doesn't have to be at 0 for the curves, right? The 0 for the curves could be where? It could be like here, right? Maybe this is C2 of 0. If they're disjoint, they're disjoint, right? But if they're not disjoint, then there's some point where they intersect, right? But you could look at, you can take, say, B1. P has to be equal to, say, C1 of T1. In Hasto, it has to be equal to C2 of T2 for some choice of C, you know? And so B1 of T, I could make C1 of T minus T1. And I could make B2 of T equal to C2 of T minus T2. See, then I have B1 of am I doing this right? I'm sorry. Maybe I want plus T1. I'm sorry. Plus T1. Plus T2. So B1 of 0 is what? C1 of T1, right? Which is P. And I have B2 of 0 is what? C2 of T2, which is P, right? And what's B1 prime? B1 prime of T is C1 prime of T plus T1, right? And B2 prime of T is C2 prime of T plus T2. Anyway, my point is that B1 prime of 0 is equal to B2 prime of 0, right? How do I know that? Because these are both equal to V of P. Remember, we're assuming these are both integral curves to a given vector field, so they have the same velocity vector at the point P. But my point is you can reparameterize the curves, get a new pair of curves, B1 and B2, which meet at 0, and then you use the theorem. It shows you that B1 and B2 have to be what? Unique, because they're both integral curves of the vector field through P. So if they're unique, that means that, and there has to be what? An interval. So this gives you the existence of the interval, which gives you part 2 of the theorem. Sorry, it's not especially exciting. I don't know why I spent so much time on it. But moving along. So the other interesting idea here is diffeomorphisms generated by vector fields, right? And all of the language that goes with that. So hopefully I think we have enough time to do it justice today. I think we'll come back to this idea eventually. Again, a vector field is called complete if you can find an integral curve that's the whole reals, right? So let's see here. Here's his example. So this is section 3.9, which is on diffeomorphisms generated by vector fields. What's a diffeomorphism? So it's a bijection which is also smooth. This is a diffeomorphism with smooth inverse. Anyway, so he says, look at the constant vector field again, right? V of P, which was what? It was, well, he's got K1, K2 at P. That's nice notation. I should use that. TPR2. So we found the flow, we found the integral curve at through P at T was what? It's P1 plus K1T. I think I did it in n dimensions over there. Sorry about that. You know how I am. P2, but certainly this is the two-dimensional consequence of my 1, right? You notice that he's slapped a sub P on here to indicate the point dependence of the integral curve. So another notation for this, he says define, hence define, check this out. So phi sub t, all right, of x comma y equal to, here we go, x plus k1 t comma y plus k2t. This is for fixed t. All right, how are these related? Can we write down a formula which links both of these silly things? So you said phi sub t of x comma y equals to c sub x comma y of t. Very good. Yeah, that's it. This is really just a repackaging. What's the difference, though? So this is the so-called time t flow of x comma y. All right. So like if I look at phi 1 of xy, what's that give me? X plus k1, y plus k2, like that, right? You could picture this, right? Suppose that the vector field k looks like this, right? You pick a point, x comma y, right? And then you can look at the flow of this point along the integral curve. After 1 unit of time, you flow up here, you know? And so forth. You flow along the integral curves. All right. Now, let's see here. Let's see here. Now, he's also claiming that this is a diffeomorphism. So, like, what's phi 1 inverse? Let's say a comma b. What would that be equal to? This is not hard. Set this equal to ab, right? Solve for x and y. We get what? A minus k1, b minus k2, right? If you think about this, you could do this for a whole set, right? You could do something like, I'm going to look at this shape, right? I'm going to transport each point in this shape. Oh, why did I choose something so complicated? You could look at each point in this shape, and and we could flow a certain amount of time, right? And this would be, to get from here to here, I could look at phi, 1 perhaps, say it's phi 2, right? To map back, I would use phi minus 2, right? And so this is in fact a diffeomorphism that's generated by this vector field. You can play this game. Although I should make it dotted, so we want to think about open sets. Indeed, there is a formula that exists. I'm trying not to erase these things, but I guess I just have to accept my fate. Ooh, I'm going to especially regret erasing what I just erased. So yeah, the critical theorem 3.9.2, I won't write it all up here. But this basically explains the bells and whistles for these flows, the critical point being this, phi sub s times phi sub t of x is equal to what? It's equal to phi sub s plus t of x, provided what? There's some fine print here. So this is for s comma t in the IP, such that we need s plus t also in the interval at p. I think this, what should this I sub p mean? He picks a point at the start of the theorem, and he says that IP is an interval containing 0, right? And yeah. Curses. Oh, fine. I realize I can't cannibalize the thing. So here it is. We have V, smooth vector field on Rn. All right. For each point, P and Rn, there exists a domain. What's a domain? What's a domain? I'm asking you guys. Domain is a technical term in here. What's it mean? Same as complex. Open and connected. We got it. That's it. So there's an open connected set in Rn, a interval of real numbers containing 0 called IP, a smooth map, phi, that is going from U cross IP to Rn, and where elements in range phi of x comma t, which is another notation for phi sub t of x, all right, such that one, if I'd been smarter, I would have scanned this. Oh well. Phi of x comma 0, by now you know I'm not that smart. Phi of x rho is x for all x in U. 2, for all x in U and for all t in IP, the parameterized curve C from IP to Rn given by C of t equals to phi of x comma t is what? Is an integral curve of V. You know what this is doing? This is just giving some technical underpinning to the picture I drew over here, really. And 3, for all t in IP, why did I write this out? And there's a reason. The function phi sub t that goes from U to phi t of U, subset of Rn is what? Is a diffeomorphism onto its image. There we go. So this is the diffeomorphism that's talked about in the title to the section. And then 4, the thing I wrote down at the start but then erased, which might give you hope if you're a student of Math 421 to make a connection, a collision between worlds, as it were. This number 4 gives us hope because it shows us something really kind of interesting, which is that for all S and T in IP, such that S plus T is in IP, we have that the flow along S and then, well, the flow along T of the point X followed by the flow along S of that point is equal to the flow of along S plus T units of just X to begin with. So, I mean, there's a group structure to be found here. If we have IP as the reals, right? Then the inverse of phi of S exists, right? Because if S is in there, minus S is also in there. So phi of S and phi of minus S, these are inverse as maps. And so if you look at it, there's a one parameter group of diffeomorphisms here. If we have that IP is equal to the reals, then if you look at this set, phi of t, right? If you look at G, this is a one parameter group of diffeomorphisms. In our current context on Rn. What's the identity? Flow by 0 is the identity, right? If you flow by 1, what's the inverse? Flow by minus 1, right? Now you got to be careful. For an arbitrary vector field, you don't necessarily have a group of diffeomorphisms because this stuff can happen over here. Not all vector fields are complete, right? So over here, I could look at the flow by 1 in this one, but the flow by minus 1 wouldn't be in here because of the nature of the integral curves. But for complete vector fields, there will be corresponding groups of diffeomorphisms. So for the constant vector field, those groups of diffeomorphisms are just like the translation group. What's that? Yes, through X. Thank you. I think that's right, yeah. so this is a neat idea, right? I mean, I don't know, if somebody told me that there's a connection between vector fields and diffeomorphisms, I don't know if I'd believe it at the outset, right? Because vector field is very much a local thing, right? But a diffeomorphism is more of a global thing. So we're making a local to global connection, right? Which means you should be able to get like some kind of Caesar credit for it or something, right? But like seems like local global. It's very very popular. There you go. There you go. I mean, this is I was talking to a colleague at another university. They've been trying to work a way to get in, like give a math talk that's sold as a local to global initiative, but in the sense that they're interested in, not the sense that the rest of the university is interested in. Local to global. You have to be careful with these kind of jokes. Some people are interested in these issues. They don't have a lot of humor. Anyway, let's see here. So, trying to think if I can explain a little bit more here. But this is basically the idea. I mean, we can find the integral curves, and we can track points along the integral curves, and we can use that to make constructions. This is in part how we'll define Lie derivatives a little bit later. So we're just trying to introduce this concept of integral curves and do a few calculations, just so that you're not blindsided by the concept of a flow when we get to it a little bit later. I don't think I've said quite enough to really, really pin it down. In fact, the exponential on a Lie group is defined. You can prove on a Lie group that the Lie groups are nice, and if you look at curves through the identity, you can look at them as one parameter groups of diffeomorphisms, and you can actually define the exponential on a Lie group in terms of some of these things. Something like the time one flow of something or other. I forget the details. I was trying to find that before class, but I couldn't find the formula, and I'm scared to just try to freehand it. So I'll just say somewhat ambiguously, you can use flows for all kinds of things. And he has some good recommendations for future reading in here, I think. But anyway, so Friday, if you still haven't dropped the course, hopefully not. All of you, especially you though, no dropping my course. Uh-oh, you're not making very committed eye contact right now. I'm a little bit worried. Friday, we will be into the wild world of differential forms and wedge products and so forth. So what we're doing Friday will be much more sort of down to earth, despite the fact it's super abstract. I mean, what I'm trying to say is Friday I'll actually be making connections with Calculus 3. So like Friday, I think what I'm going to try to do is show you about one forms and two forms and how we can use one forms and two forms to encode like vectors. There's two different kinds of vectors. There's polar vectors, there's axial vectors. We have correspondence between one forms and two forms and vectors and so forth. So I'll try to explain that Friday as best as I can. So I'm not going to, probably will not follow the book too closely Friday. Technically we're in chapter 4, but I think to start with I'm just going to tell you my heart on it and then we'll go from there. Oh, and I also need to, of course, send you guys the, hey, here's what's on the test next Monday, right? Because we have that pesky test coming up. Yeah. Yeah. So anyway. All right, with that, I better shut up because I got to get home. Oh, yeah, thanks.